Okay, so I am R. Srinivasan. I am also called as Vasan. So I am supposed to teach you. I'm supposed to teach you this graduate analysis one for you. I'm actually teaching graduate analysis one and graduate analysis two. So some of you, so there is a prerequisite for this course, which is some basic analysis. And I see many of you are CMI students. I mean, those who have done the previous year in CMI. So those people will be knowing this prerequisite like metric spaces and all. But there are minimal prerequisites you need for like metric spaces, basic function theory, limits, and all those things. Those things I am sure all of you will know. So some of you are from in MSc also. There are some students from CMI. There are some people are from outside. I mean, those who have joined from somewhere else from universities, and I think they must have done this prerequisite. So this course, so this I'm going to do two summers. I mean, I'm going to do graduate analysis one and graduate analysis two. And some of the BSc students may not opt for graduate analysis two. So I will tell you what I will do in the graduate this course. So, so in this course, there is a syllabus in CMA website. You can see there is a syllabus written in CMA website. And I will more or less follow that. And not exactly more or less. I will do slightly more than what is mentioned there. Slightly more than that. I will do everything which is mentioned there. And I will do something more. And something more means some of the things which are postponed to next semester, I will do it in this semester. And there is something called Hahn-Banach theorem, which is only the statement. I mean, it's mentioned that only statement has to be given, but I will give the full proof. And few things I will do more. And mostly I will do, I mean, actually there are only 15 weeks for this semester. Usually it will be 17 weeks, so we miss 4 classes. But still, I think I will be able to do everything which is mentioned in the syllabus. So we will start with what is called a measure theory. Then we will do some functional analysis. We will do Hilbert space theory. We will do some Banach space theory, then some Hilbert space theory. Then we'll come back to some measure theory. Then we will do some Fourier analysis. That's what is the idea. That's what the plan for this course. So in the next semester, so those who want to know about the next semester, it's basically there will be few theorems. Actually, some of you who have done analysis course in CMI must be knowing those theorems like Arcela-Ascoli theorem, Schoen-Weierstrass theorem, all those things you know. But still, if everybody knows, then I will not do that. But if some people have not done that, then I will do that. So after doing that, then we will basically do functional analysis. So that our aim of the next semester would be to prove what is called a spectral theorem for a normal operator. If you look at the syllabus mentioned in the CMA website, it is for spectral theorem for compact normal operator, but I will prove for general normal operator. So so for that we need some more machinery, like some operator algebraic technique, like C-star algebra and other thing, with very minimal. So I will introduce that and I will prove the spectral theorem for normal operator. That is a plan for next semester. Okay. So, okay. So some people asked about, so in this semester, I will do first measure theory. I will start with measure theory. So I will introduce what is a measure and is there anybody waiting? Let me just check. No, nobody is waiting. So I will first introduce measure and then integration with respect to a measure. Then we will go to some functional analysis. We will do some Banach space theory, Hilbert space theory. Then we will come back to measure theory again. Few things in measure theory. Then measure theory provides the example we need to do functional analysis. So that's why we do measure theory first. Then finally we will do some Fourier analysis. So some people were asking about how the grading is. So the thing is, those people, I mean, some of you have done analysis 3 with me. So usually my exam will be something like there will be lot of choices and there will be, the mark will be usually set for some 200 marks. But I cannot do it now, do that now. See, in my question paper, there will be a part A. Part A will contain what we have already done in the class, and part B will be some new problems. But I cannot, since we are going to have an exam online, midterm exam and end term exam online, I cannot give you the problems which you have done in the class. So what I suggest is the following: you will have midterm and end term, but I will ask you to present something. So I either during the class time or when or some other time. I mean, it depends on how much time we have. So maybe some other time I will ask each of you will present something. So my idea is you have to understand the proof of the theorem and also you should be able to solve problems. So that is how the exam should be. So I will ask you to present something. So that will have some great marks, and then there will be midterm exam, end-term exam, and there will be some assignments. So which you will all post online either through Moodle or when I get to Moodle, or you will send it to me by email. Okay. So as I said initially, when some people were not there, I will start writing this. I will start writing when I get my iPad. I'm waiting for my iPad. So when I get it, I will start writing. Now I have only the laptop, so I'm not able to write it. I will share a file today, and we will go through that. So before that, let me say something about this measure theory before sharing that file. So what is this measure theory, and why are we doing this? Once again, let's close this participant. Okay, so what is this measure? So you have done some metric space theory. So in this metric space theory, what do? You have 2 points, and you will define a distance function. Distance between 2 points, and that is an abstract distance function in the sense that if you have if you have any set, then you between 2 points in that set you can define a distance. So how do we define? So usually we have a distance that satisfies some properties, like it is positive and it satisfies triangle inequality and it's symmetric. And using those properties, you extend. You define an abstract distance function. Like that, we have something like a measure in our real world. Like we measure length, we measure. We can measure a length of something, or we can measure area, we can measure volume. So we want to generalize this. We want to abstractify these ideas, this idea of a volume or measure. And it's not, so suppose if you have a straight line, then you want to define a measure for any subset of a straight line. For us, the straight line can be the real line. Then you want to measure the length of any subset of a real line. Any subset means it can be anything. It's like rational numbers, for example. So so if you have a single point, what will be the length? The length will be 0 for a single point. But then a rational number is countable, so you can write the set of rational numbers as union of singleton set. Okay, so you want to if you want to define length should have some property. If you have 2 disjoint segments, then the length of 2 disjoint segments should be the length of the individual lengths. So you will have some property for this length. Similarly, you have some properties for area, or volume or something. And that is what we want to generalize, and we want to define. Measure is something, the generalization of this kind of concepts. For example, measure, but then area, length, there is some uniformity for that. So if we have a length of some interval AB, and if you have some interval CD, suppose this, what is the length of an interval AB? Length of an interval is just B minus A, or the length of interval CD is D minus A. If B minus A, it only depends on the B minus A or D minus C. It does not depend on where that interval is. The length is some sort of uniform, but the measure can be non-uniform. For example, if you drained yesterday and you want to measure the amount of rain in different places of, see, what will we do is we define something called a whole set, a universal set. For example, Chennai is our universal set. And you want to measure how much it rained in one place in Siriseri and how much it rained in somewhere else, somewhere in Mandavili or somewhere. Then it does not depend on the area of this place. It can be different in, the rain can be different in different places. So this is some sort of idea of measure. So a measure need not be uniform. It is some way how a mass is distributed. You can say that how a mass is distributed in a set. Okay. So that is how the measure is. We will define the measure. We will define the measure clearly when I share that file. So why do we want to do this? So we want to do, so the basic reason we want to do is, one of the basic reason for defining measure is, of course, when you want to do probability theory, then you need the measure theory. When you want to do the probability theory in a very rigorous way, then you need measure theory. Or so the basic idea is, if you want to develop integration, so you know Riemann integration, but then Riemann integration does not, it involves measure, but you don't know that it involves measure. It can be defined through some upper sum, lower sum, using some limit. And when you know the limit, then you can define Riemann integration. But then the problem with Riemann integration is the collection of functions which are Riemann integrable is not some very nice class. I mean, in the sense that you cannot say, I mean, you see, when we do functional analysis, there is some objects called Hilbert space, Banach space. The set of all Riemann integration function is not some, you cannot describe it as a nice analytic object. Okay, they don't form a nice object. So then there is a problem that if you take limits, for example, see, suppose you have a collection of sequence of Riemann integrable function. Each Fn is a Riemann integrable function, and suppose Fn converges to F pointwise or something. Then is it true that integral? Can you say that when integral Fn converges to integral F? I mean, in the Riemann integration. So this is, first thing is, it's not clear. When, I mean, you can actually say, because we know some measure theory, we can actually say, but then there are 10 theorems which will determine when integral Fn converges to integral F, if Fn converges to F. But then those theorems within the theory of Riemann integrable function, it's not possible to prove, as far as I know. I mean, you can try that. You need to have a larger theory, like a measure theory, to prove those theorems. Okay, so that is why we do measure theory. So in measure theory, it all follows very naturally, automatically when you do measure theory. So this is the natural way of doing. So whenever mathematics develops, what is natural? See, in mathematics, we may find some concept, but we may think that is natural, but that may not be natural. When we develop the concept, we will think this may be the natural thing. Okay, so what we do measure theory is the actual natural way of defining integration. And this is a more general way. And Riemann integration, all those things will be Riemann integration. I mean, we will, for example, we will develop something called Lebesgue integration. I mean, which is with respect to some particular measure called Lebesgue measure. Then the Riemann integration is just a particular case of that. When restrict to some particular class of function, that is what is Riemann integration is. So that's what we want to do. And another thing with Riemann integration is there is this product integral, double integral, triple integral, which is not, there is no nice theory which explains that product integral. I mean, it is done in which you will see. There is something called Fubini's theorem. So such a theory is not. I mean, such a nice way. It's not there in the Riemann integration. So when you want to do the product, this is the. So you will when we do measure theory, you will get convinced that measure theory is the right way of doing. I mean, it is through measure theory. It's the right way of. That is the right way of doing integration. So that's what we want to do. So as I have introduced now, so first what we want to do is introduce measure. So in mathematics, whenever a measure or a metric or a distance function or whatever, we will define it as a function. So this is a measure is a function which we want to define on a collection of sets. So you have some holes. See, whenever you want to do mathematics, there is something called a universal set, and you will deal with subsets of that universal set. So, but then can we define? So the distance function is defined between 2 points in a set, but this is defined on a set. Okay, you want to measure a set. Measure is on a set. You want to define. So if you have a real line, you want to measure the area length of a subset, length of a line segment, a subsegment or something. So then this measure should satisfy. So then you can define any function. So you want to define a measure on a collection of subsets, but then it has to satisfy some properties. For example, if we have 2 subsets which are disjoint, then the measure of the union of these 2 subsets should be addition of the individual measure, individual length or something. So that is one property. Then we may require some sort of continuity property. If we have a big set and you can approximate it as increasing union or decreasing intersection, then the measure should also decrease to that. And the measure, I mean, when you approximate by decreasing intersection, the measure should decrease to that, or increasing union, the measure should increase that. So this is some sort of continuity we want to have for the measure. Then if you know the measure of some, we should know the measure of the whole set, which can be infinity. So one thing is a measure can take value infinity. For example, the measure of length of the whole real line is infinity. So it can take value infinity. And the measure is always positive. I mean, it can be, well, it can be negative, or it can be even complex number. Later, we will see complex measure and other thing. But now we want to talk about, we were only generalizing the concept of length. So we assume that the measure is always positive for the time being. Later, we will deal with signed measure and complex measures. So the measure is positive, and it should add up for disjoint set. And another thing is you should know the measure of the whole set. And so when you know the whole set, then if you have measure, if you know measure of some subset A, and you know the measure of the whole set, then you know the measure of the complement. It should be just the measure of the whole. I mean, the complement should be, you should have the measure of the whole set subtracted by the measure of this set. See, that should be the case. If you have a measure mu, then mu of A union mu of A plus mu of A complement should be measure of the whole set. Okay.
Sir, I have a question.
Yeah.
So you just said that measure is a function
Right.
from a collection of subsets. So it is the collection is with respect to some given set, right? So we are taking a set and
with respect to me, that is a universal set. It's a collection of subsets of a universal set. You can talk about the area. Okay, you can talk. So you want to generalize the area, then you will have R2, R cross R2. So if you take the subsets of R2, then you can. I mean, you should be. I mean, see, our idea is to define for any subset of R2. The subset can be very complicated. It need not be circle or triangle, or I mean, it need not be even an open set or something. You know, open set, closed set. It need not be even like that. The set can be very complicated. Okay. So, and when we want, so the question is whether we can actually define on all subsets. Sometimes it's not possible. The reason we cannot define, we can actually define on all subsets, but then that may not behave nicely. We want to have some properties for the measure. It has to add up for disjoint set, and we want some continuity for the measure, and those things may not, the measure may not satisfy those properties. So in order to do that, we may have to restrict to a sub collection. It's need not, I mean, if you have a discrete set, then we can define on the power set. We can define on all subsets. But when we have a continuous means like real line or something. So when we have a real line, then we may not be able to define the measure on all subsets. We may have to restrict to a subclass. I mean, a class of subsets. So that is why. So what kind of sub collection we have to deal with? That's what we want to see. For that, we have to define some notions called sigma algebra. Why we need it is because that is where we want to define our measure. Okay, we cannot define it on the whole, all subsets or the power set. So for that, we need to define what is called a sigma algebra. So this is just a motivation why we deal with some collection, why we define something called sigma algebra, which I'm going to define soon in the next few minutes. So that's because we want to have some properties for the measure, we should be additive, sigma additive, and for that we need our collection has to be closed under those things, union, complement, and all those things. So that is why we deal with those kind of subsets. And then the measure should satisfy some property. Then we will, so after defining measure, we will derive the properties of the measure. Then we will start doing integration. Before doing integration, we cannot integrate all functions. So we can integrate only some particular kind of functions. So we will define what is called measurability and then start integrating those functions. So now I will share a file. I will send you this file. I mean, if some people are used to taking notes, you can take notes. I don't mind. I mean, it's up to you, but you need not take the mind. I will send you this file. So once again, I will get that.
Are there any TF for this course?
But say it again. Yeah. Yes. What did you ask? TA for this course?
Yeah, yeah. Are there any TA for this course? Who?
Yeah, there is one person. I mean, I don't really need a TA. I mean, because
Okay.
I will be doing. I mean, there's one person as there's Chellapillai. There is a PhD student. He has opted for this. So nobody has contacted me. I haven't asked anybody. So he contacted me. So currently he's the only TA. If somebody else contacts me, then he will also be. So I hope all of you can see this file, which I have shared now. Can everyone see the file? If anyone can't see, then you tell me. Otherwise, I will assume everybody can see this file. You can see the file?
Yes, sir.
Yes, it's visible.
Okay. Okay. So today I will not write anything. So I will, I mean, there is a possibility that I may go fast because something is in print. Because I'm not writing. So you have to stop me when I'm going fast. So as I said, we plan to, what we want to do is we want to define measure space. So measure space, we will come to that later. So a measure space is something, it's a tuple, like metric space. What is a metric space? You have a set and you have a metric defined on that. Like that, measure spaces, you have a universal set, some sets X, and you have a collection of subsets of that set. It's a collection of subsets of that set X. Then you have defined a measure on that collection. So that is what a measure space is. So we will define that in the end of this class. Hopefully, if you have time. So this is the preliminary. So we want to, so before starting, as I said, we want to define what is called an algebra and a sigma algebra of sets, okay, as a collection of subsets of something. Okay, so we will be dealing with a universal set always. So we have a so this is okay. So we have a universal set X here, okay, which is a non-empty set. Of course, we want to do non-trivial measure theory. So this is a non-empty set. And then we have this P of X is the power set of that, okay. So then the set of all subsets of this X. And this phi denotes the empty set, of course. Then all of you know what is A complement. A complement is elements which are not in that. So we will be dealing, I mean, since the start of the measure theory, we will be dealing a lot with sets and proof using sets. Okay. So I hope all of you are quite familiar with this kind of sets. I mean, I'm sure all CMA students are familiar, but others also, and I hope they are also familiar with that. Then we have this De Morgan's law. I mean, which is when you take the complement, it will become the intersection of the individual complement. When you have the complement of the whole union, then it's an intersection of the, which holds for infinite collection also. You can take infinite union, infinite intersection. So that also it's you can do. So then the De Morgan laws goes through. So here is something defined for, if you have a collection of, you have a sequence of set, then you can define a limit of, I mean, limit may not exist. You can define a limit for the collection of sequence of set. So that to define that limit, you have to define. So it is usually like we define the limit in the case of real numbers or complex numbers or in limit. So the limit is defined through what is called, first you have to define what is called a lim sup, and you have to define a lim inf. If the lim inf and lim sup are coincides, then we say the limit exists, and that is the limit of that. Okay. So the lim sup is defined like this. We will come back to that. You need not really remember this now. You have a collection of set AM. AM is a collection of subset, a sequence of sets. Okay. Then you take the tail part of this. So tail means it's a union from m equals. So you can see that it's a union from m equal to n to infinity. Okay. Then you take the intersection of that from n equal to infinity. So this is you take the union of AM from n to infinity. From n to infinity. M varies to n to infinity. Then you take the intersection from n to infinity. So you interchange this is what is called lim sup. To define lim inf, you take the intersection between n to infinity, the tail intersection, and then take the union from n to infinity. Okay, so this is what is called lim inf, and this is what is called lim sup. When the lim inf and lim sup coincides, then we say the limit exists. Otherwise, it's lim inf and lim sup will always exist because this is defined. This is well defined. Okay, this is so this is like your union is like a supremum, and your intersection is like a infimum. So this is where, as given in the bottom of as a footnote. you can see that this is very similar to the lim sup and lim inf defined for real numbers. So you take the supremum of m greater than n, either the tail, supremum of the tail, and then you take the infimum of all those tails. So similarly, you take the infimum of the tail and then take the supremum of the all those tail. So that is what is called lim inf, and this is what is called lim inf. And when lim inf and lim should coincide, then we say the limit exists. So this is about lim inf. So we will come back to that. You need not really remember this, but the idea is you take the union for the, you take the supremum. Supremum is like union and the infimum is like intersection. You take the supremum of the tail part, then you take the intersection of all the tails. Okay, so this is what lim inf and lim sup. If you don't see the whole screen or something, you tell me, because when I press, yeah. Can you see the whole screen? Whole file?
Yes, sir.
Okay. So there are some properties of lim inf and lim sup. So as easily checked, lim inf and lim sup consist of those. So when you define the lim inf of a real number, what does it mean? So the lim inf of a real number is defined like lim inf and lim sup is defined like this. So what is what do you call as a lim sup? A lim sup of a sequence of real number is so how will you define a lim sup?
It's
Okay.
like smallest real number which is like larger than all the numbers that is in the set.
What is
And
it?
now, like it is the smallest real number x which is larger than all the real numbers in the sequence, and such a real number exists by the completeness property.
Right. So here you can see. I mean, so, can you just look at it and can you guess something? So you have, see, the lim sup is something like it. It has to be in the intersection of all these things. So it has to be in the tail part of. It has to be in the tail part for all the AMs. It has to be in all the tail. That means it has to be in one of those AMs. See, one of those AM in the tail part. That means what does it mean? A element is, so this is lim sup of AN is a set. So something is in the lim sup if it is in infinitely many of them.
So for real number, we can say that it is the supremum of infimum of the tails.
Correct. Right.
And
No. So I'm saying, I mean, then see, you will say that something is a lim sup if I mean, let us forget about that. It's clear when you look at the set, lim inf of the lim sup of a set. If something is in the lim sup of a set, lim sup of a sequence of set, what does it mean? That means that it is in this intersection. It is in the intersection mean it is in all the tails, all the tail. That means if it is in all the tail means it has to be in one of those AMs. That means the element has to be in infinitely many AM. That's what it means, right? If we have a X which is in AM for infinitely many of those AM, then that will be in the lim sup. Lim inf, for example, on the other hand, lim fin means it has to be in the union. So it has to be in one of those tails. It has to be in one of those tails. That means after some time, it has to be in all the AMs, right? So if an element is in lim in, if it is in one of those tail, that means one of the tail means the intersection of the tail. Here the tail is different. This is the tail of the tail means union. For the lim in, the tail is the intersection. So some element is in the lim inf, some X is in lim inf. If it is in AN after some time, if it is in AM for all M greater than or equal to, there exists N such that X is in AM for all M greater than AN, correct? It should be after some time, it should be in all the set. That is what a lim inf is. Lim sup is, it should be in infinitely many of those AMs. So if it is in some AM after some time, it will be in all of them. So it is clear that lim inf is always contained in lim sup. Maybe I will show this here so that it will be, you can see. It says that it can be easily checked that lim sup consists of those elements of X that belongs to infinitely many of AM. So I was just going through the proof. So something is in the lim inf. It is, lim inf is just the collection of all elements in AN, I mean all elements which are contained in infinitely many of the AM. See, suppose something is in infinitely many of the AM, then it will be in the union of this tail, union of, I mean, this union tail. Then it will be in the, then it will be in the intersection. So then it is in the limb soup. For limbs, it has to be, after some time, it has to be in all of them. So respectively, something is in the limb in, if it belongs to all elements of AN, except perhaps after some finite time, after some finitely many set, it should be in all of them. It should be in the intersection, it should be in all of them. So if it is in all of them, that is certainly in the infinite. So if some element is in limb inf, then that is in limb soup. So limb inf is contained in limb soup. So is it clear? I'm actually not seeing anyone. So because I am not able to see the file, so I have reduced the size. So I am not looking at you. So you have to tell me whether if you don't understand. Okay. So I think it is clear to everyone that limb inf is contained in limb soup.
Yes, sir. Yes.
Okay. So since you agree, so what is the next? See, it is easy to check that if AN is in. So if AN is increasing, for example, if AN is increasing, then you can see that if AN is contained in that, then you know that what is it? So then AN is increasing, then when AN is increasing, then the limit then this, so intersection of AN, I mean, you will see that that the limit is just the union of those things. When it is decreasing, it is just the intersection of those things. That just follows from this. If AN is increasing, then this is just one of them will be just AN. Okay, then you are just taking AN is decreasing. This is just AN. It starts with AN. Then it is just the intersection of that. You can see that similarly. This is also if it is intersection, then this is basically this thing. Is it clear that if it? I mean, I will leave it as an exercise. So it will be clear that when it is increasing, it is just this union. So when it is increasing, it is just this union. When it is decreasing, it is just this intersection. Okay. Anyway, these things we will come back to this again, because when we do that, but actually we want to define what is called an algebra and sigma algebra. This is just a preliminary. So this is not needed now. We will come back to this. So what we want to do is we want to define algebra and sigma algebra. Okay. So why we want to do that, I have already told you that we want to define a measure and we want to have a sub collection of the power set, sub collection of all subsets, which satisfies, so that we can define a measure and the measure will satisfy some of the properties. So we say that something is an algebra, with a collection is an, one second, I will just come. I'm sorry, I'm teaching from my house. So, okay. So to define a measure, we have to define what is an algebra and what is a sigma algebra. So this is the definition of an algebra. So actually we want to define our measure on what is called a sigma algebra. Okay, that's what we want to define it. But before defining it, this algebra is just a tool. We will not be using it to define our measure. What we will be using is
Yeah, possibly that's irrelevant, but like is this algebra in any related to the algebra that is done in the like ring theory and stuff? Like a set is called algebra if G is there and if G is there.
No, there is some property, but this is a collection of set and see this is what is some sort of this is something similar, but you don't have addition or something. No, you have something replaced by union and something replaced by something. I mean, there is some connection. I mean, there is some, you can analogous notion you can relate, but it's not precisely that.
Okay, guys.
So this here is an algebra. You have a collection is called an algebra, here also you have an operation on sets. So if you say that it's an algebra, so it's like the identity element. You have an empty set. In that collection you should have empty set, and you should have the whole set. Okay, so you have an empty set and whole set. And if you have A and B are there, then A union B has to be there. And if A is there, then A complement has to be there. You can say that this is like an inverse or something. I mean, you need not worry about it has anything to do with the other algebra. This is an algebra which is a collection of subsets, okay, which satisfy this property that if A is there, then A complement is also there. That is because when we want to define a measure, when we want to assign a measure for A, then we should know the measure of A complement. Okay, so that is why A is there, then A complement is there. So if A and B are there, then A union B should be there. So an empty set should be there, and then the whole set should be there. So this collection is what is called an algebra. So this is just a collection of subsets. So we will deal with universal set X, and this is just a collection of subsets. Okay, and that subset satisfies this property. So you can immediately see using De Morgan's law. If A is there, A complement is there. Then A and B are there, A union B is there, so the A intersection should also be there. That's very clear. So when the intersection is there, you know what is called a symmetric set. I mean, there is a minus B. So I don't know whether A minus B is defined there. And A minus B is A intersection B complement. Okay. So you remove the part of B, that is what is called A minus B. So a symmetric, I mean, we will get to it, I mean, when we do that. There is something called a symmetric difference. So if you have two sets A and B, you can take the intersection A and B. You can take A intersection B complement. Okay, that is what is called A minus B. That is, you subtract the B part, you remove if you have a Venn diagram, if you draw a Venn diagram, maybe I will show you. Is there a chat? So, I mean, I will not look at chat while doing this because that will be disturbing. Someone asked whether I will be sending the file. Yes, I will be sending the file. But when I ask you some question or something, we will use chat. Okay. Okay. So I thought I can write it somewhere. I don't know whether I can actually write. So if we have a set like this, okay, then you have call this set as A or something. Then you can have another set like this, say something as B. Then you can just A minus B is just this set. Okay, this part. Okay. So, and then symmetric difference between these two is you just remove this intersection, just these two parts. A minus B is this part, B minus A, this part. A minus B union B minus C is just this part, okay, and this part. You just remove the intersection, okay. That is what this A minus B is. So that is what the symmetric difference is, okay. It's very clear when you draw the diagram. Okay? And as you can see that if you have, algebra, then if A is there, then A is there, B is there, then B complement is there. So A intersection is there. So A intersection B complement is there. So A minus B is there in the algebra, and the unions are there. So A minus B union B minus A is also there. So the symmetric difference is also there. So from using those axioms, you can actually say that symmetric difference is there. Similarly, by induction, if A1, A2 up to AN is there, then A1 up to the union, finite union is also there. So using this thing, you can see that finite union is there and finite intersection is there. But countable union may not be there. So as I said, we want to define our measure on what is called a sigma algebra. But we need this concept of algebra because when we want to construct the measure, we see usually the sigma algebra may be very complicated. A sigma algebra, usually we will not define, we will not explicitly give you what is a sigma algebra. So usually we will say sigma algebra is something generated by some collection of sets. So we will be defining our measure on the generators. Then we want to extend our measure from the generator to the whole sigma algebra. So when we want to do that, we will be usually defining at an algebra. Then we will extend to a sigma algebra generated by this algebra. So that is why we need this algebra. Okay, so this algebra is where we will define our measure originally. Then we will extend our measure from algebra to. So this algebra is a tool. It's not something which which we will use in the theory, measure theory. This is a tool where we will define our measure. Then we will extend from algebra to sigma algebra. So this is the definition of algebra. I'm sure everybody understand what an algebra is, which is a subset which satisfies this property. Then we can define what is called a. I'll just erase this. So if you have an algebra, a sigma algebra is something which satisfies one more additional property. You can have a sequence of sets from that collection, and the union of that countable union. It's not uncountable union. It has to be a countable union. The countable union is also there. So that is what is called a. I don't know. My thing is not moving. So, we have defined algebra. A sigma algebra is which satisfies all the properties of the algebra. And then additionally, it satisfies, if we have a sequence of elements, then the union of those countably many elements, then the union is also there. So it is closed under countable union. Yeah, I don't know why my screen is not moving. Okay, I think it's moving now. Oh, when I have that, it's okay. Yeah. So an algebra. So a sigma algebra is something which satisfies all. It's a collection of subsets which has empty set, which has the universal set, and it is closed under union. It is closed under complement. Further, it is also closed under countable union. You have a collection of sequence of sets. Then union of n equal to infinity. An is also there. This is what is called a sigma algebra. So by De Morgan's law, if countable union is there, then the countable intersection is also there. So then the lim-inf is defined by some countable union and countable intersection. Lim-inf and lim-sup, that is how it is defined. So the lim-inf and lim-sup of collection of sets is also there. And if the limit exists, then the limit is also there. So the sigma algebra is something, a general object than the algebra, where the limit also is there. Okay. So now let us see some examples of algebras in sigma algebra. The simplest algebra or sigma algebra is a power set. For example, you take all subsets, of course, that is closed under union, complement, and everything. That's a sigma algebra. You take just two sets, empty set and the whole set. Of course, if you take the union, you are going to get one of these things. If you take the complement, it's closed under complement. This is a trivial case. This is the smallest sigma algebra. This is the biggest sigma algebra. So, okay. So these are all trivial case. So let us see some other non-trivial examples. Okay, the non-trivial examples.
So can you please show the definition of sigma algebra once more?
Yeah, definition of sigma algebra is nothing but it's an algebra which is closed under countable union. That's all. Where is it? Sorry, it is here. It's here. It's here. It is this property. You can see my mouse. So it is just this property.
Yes,
it's closed and countable union. Okay, that's all. So whenever you don't understand, you can stop me. Okay, or you want to see the slide or something, you can stop me. Okay. So it's closed under countable union. That's all. Yeah, algebra is only finite union. Sigma algebra. See, sigma is always for countable. Whenever you use sigma, this word sigma weak topology or whatever, we will see later in the next semester, maybe some sigma weak topology or something. Whenever we have a sigma, that means it has to do with some sort of infinity. Okay, so it's countability or something. So here you have a countable infinite, countable collection of set. Then the union of those sets and intersection of countable collection has to be there. That is what is called a sigma algebra. Okay, so let us see examples of algebra. So if you have, here the whole set is just the interval 0, 1. You can take you can take real number. The same thing work with the whole real numbers. Then you take finite union of this kind of intervals. For example, if you take open interval, it will not work because you have to take the complement, it will not work. You take finite union of half closed, half open interval. It is closed in this is left, no? So it is closed in the left. It's a closed interval in the left and open interval in the right. Okay, you take this kind of interval then you take finite union of such things. Okay, you take finite union of such things. Then such a thing, if you take the complement, I mean, the interval can be, I mean, okay. If it is real number, the interval, you have to allow infinite interval also. So here it is only 0, 0, 1. So if you take the complement of this, you show that you take any interval like this, I mean, AI, BI, where it is closed in the left and open in the right. If you take the complement, that will also be closed in the left, and if you that will be finite. I mean, what is the complement of this? It's complement of one single interval like this. That will be 0 AI, then union of BI1, right? That is the complement of this. So if you take the finitely many union of that will also look like that. It will be maybe a bigger finite union, but still it will be a finite union. Okay. So if you take this kind of interval, then the complement is also there. And of course, empty set is there because you take AI equal to AI, then no, you have to add empty set. No, empty set is also there. No, empty set is not there. The whole set is there because you take the AI equal to 0, 1 there. You have to add empty set, I think. Yeah, so he says that. So it is just the A0 consists of empty set. You add empty set and then take this collection. Then this is an algebra. You can take union of such things. Then it will be again a finite union of disjoint, finite union of such intervals. Okay, not necessarily disjoint. So finite union of such interval. So this is an example of an algebra. And you can see that this is not a sigma algebra. I mean, you can take infinitely many disjoint union. For example, if you, so for example, I don't know whether I will be able to write it. Let me try to write it. You take something like this. You take an interval like this. Some what I want to do, I want to get a minus 1 by n, okay, some b, okay. If you take the union of these things, this will not work. So I will take plus here, plus, and if we take the intersection of these things, countable intersection, I mean, if it is closed under countable union, it should be closed under countable intersection. If you take the intersection of this, okay, that will give you the open, you will check that if you take the intersection of this, the infinite intersection, then that will give you the open interval AB. It will not give the closed, I mean, it will not be closed in the left. Okay. It is all those, if you take the intersection, it is all, this starts with A plus 1 by n to B. Okay. So if you take the intersection of all these things, then it will give you the set AB.
But we have the condition that BI is greater than AI.
Sure, right. I mean, so 1 by n.
Sorry, not that.
A plus 1 by n should be less than B. Okay, I mean.
Yeah, AI plus 1.
Yeah, that's right. When you give the example, you be careful. So I'm just giving you an example. Okay, after you start with the n, so that the A plus 1 by n is less than B. Okay, so yeah. Then you take the intersection, you will get them. I want to see, because you are only taking intersection, so you can start with after some time. So I mean, if it is not that, then it will be empty set. Okay, I mean, if A plus 1 by n is greater than B, then there is nothing between them. That's just empty set. Okay, so it is.
Okay, sorry, I thought you were taking unions.
No, I am taking intersection.
Yeah.
I mean, only the intersection will give here AB, no?
Yeah, got it.
So you have to take the intersection here.
So are we trying, like, what are we trying to prove here?
I am trying to prove that this is not a sigma algebra. Countable
okay,
intersection
fine.
is not there. Okay?
Fine.
Okay. Or you can go here and take B minus 1 by n, and then it will give you a closed interval here. Okay. I mean, you want to, you can do whichever the way you want. Okay. So anyway, this is a counter example where the countable intersection is not there. Okay. So this is not an algebra. So if you take disjoint union of half closed, half open interval, then that is a algebra, but that's not a sigma algebra. Okay. So let me erase this. Okay. So now let us consider some other class, which is indeed which is also which is which is also an algebra. right? So you take all collection of, you take set S, X, then you take a collection of all sets A such that A is either finite or A complement is finite. Okay. You can take, for example, natural number and you consider all collection of finite set, or you can take the complement is finite set. Okay, I mean, you have to include complement. So that's why either A is finite or A complement is finite. Then of course, if A is there, then A complement is also there. And if you have finitely many union of that, if you have finitely many subsets, then the complement will be, I mean, then the union, if you have finitely many of them, then the complement will be finite. But some of them is infinite. It's stable under finite union. So if you take one, so you have to consider different choices for this. If A and B are, if A is finite, then the complement is, I mean, A is finite and B is, I mean, you have to sit and check each and everything. I mean, okay, shall I leave this as an exercise, these two things? These are all some, I mean, you have to sit and check each and everything. That different choices. A and B are finite, then it is clear. A and B both are, both complement is finite, then the other complement is also finite, because that will be just the intersection. Then you have to take one of them to be complement is finite, the other one is complement is finite. Then you have to, then this will be infinite, but the complement will be finite. Complement will not be finite. What will be that? A union B complement. A union B complement. We are only checking the A union B complement. That will be fine. Okay. So similarly, you have to do the countable thing. This is also the same thing. I think this is something. So this is an algebra, and when you take either A complement countable or A complement is countable, this is a sigma algebra. Okay, this is a sigma algebra. A is a sigma algebra. This will be closed under countable union. And I leave these two things. Should I give it as an assignment? So yeah. So this example, the example 4, I give it as an assignment for you. So to verify that this is a sigma algebra. Okay. So this is one example. So this I give it as.
In this problem, you don't need uncountable, right? I mean, it will anyway be a sigma algebra.
What is uncountable? Which one you want?
So
to
in part 4, you start with an uncountable set. For countable, it will be anyway the trivial.
No, that doesn't matter, and that is not needed, I think. Yeah. I mean, if it is countable, there is nothing like this, no? Then all subsets will be there.
Yeah, that will be the power set.
Yeah. So sure. So you want to say something like, you want to say something non-trivial, no? You don't want the power set. So you want to talk about non-trivial sigma algebra. That is why you take an uncountable set. Then this will be a proper sub collection. Okay. Proper subset of the power set. Okay. So I leave this as an assignment. Okay. If this is an easy assignment. So if you have an uncountable set, then you define something like this, then show that this is a sigma algebra. All you have to prove is basically you have to check that it's closed under countable union. Okay. I think that is what he has given us exercise. It's clear. We have already seen that the first one is not a sigma algebra. Then the second one is this is also, first one is trivial thing. First one is sigma algebra, of course. Second one, this fails to be a sigma algebra. This fails to be a sigma algebra. This is a sigma algebra. Okay. So it's better you write the fourth one as an assignment. Okay. Okay. So then there is a property of sigma algebra. As I said initially, as I said some time back, that we will be defining our sigma algebra. We will not, so here we have defined sigma algebra explicitly, but when we talk about real line or something, then we will not define our sigma algebra explicitly. We will usually define it as something generated by some sets. Okay. So we want to talk about sigma algebra generated by some collection of sets. Okay, so something here itself we have an algebra. For example, we have an algebra which is a finite union of disjoint half closed half open intervals. So we will consider sigma algebra generated by this algebra. So what is the sigma algebra generated by this algebra? So which is just the intersection of all sigma algebra containing that set, containing that collection. That is what is sigma algebra generated by that. That will be the smallest sigma algebra containing that. So generated, I mean, sigma, whenever we say something is generated, it is always the smallest sigma algebra generated by smallest sigma algebra containing that. That's what we call as sigma algebra. And that is indeed the intersection of all the sigma algebra. So to do that, so first we take the intersection of sigma. So if we take sigma algebra, then the intersection of sigma algebra is also a sigma algebra. Of course, union is not a sigma. I mean, if you take union of sigma algebra, that's not true. But if you take intersection of sigma algebra, then if A is there, then A is in all of them, then A complement will be in all of them. So A complement is there in the intersection. So similarly, you can say that A1, if you have a finite collection or infinite collection, which is in all of them, then the countable union is in all of them. So it has to be in the, that's what it means by it is in the intersection. So it's easy to check the intersection of all sigma algebras, including some K. I mean, in the intersection of sigma algebra is a sigma algebra. And if you have a collection K, which is not a sigma, which need not be a sigma algebra, you have a collection of subsets, which is called the script K, which is the collection of some subset. Then the sigma algebra generated by K is the intersection of all those sigma algebra. So what is the property of this sigma algebra? The sigma algebra generated by K is that this is the smallest sigma algebra containing K. What does it mean? What does it mean by smallest sigma algebra? If we have some sigma algebra which is containing that K, then that sigma algebra contains the sigma of K. I mean, that's what it means. If you say, if you have some, maybe I will try to write. I don't know whether I will be able to write. Let me try to write. So if we have some, this is a sigma algebra. Okay. Suppose this contain that script K. Okay. Whatever that script K is, then, I mean, I'm not writing then because I may not be able to write. Then this contains that sigma of K, right? Okay, that's what it means by this is the smallest sigma algebra. Okay, the sigma of K is the smallest sigma algebra containing K. That means that if you have any sigma algebra contains K, then this contains the sigma algebra, the sigma algebra generated by that. That's what it means by that is the smallest sigma algebra. Okay. So suppose something is a sigma algebra, then that itself sigma algebra, the smallest sigma algebra containing that is that itself. So the smallest sigma algebra is that. So if we have, and the smallest sigma algebra, in fact, the smallest sigma algebra is just the set containing the collection has empty set and the whole set. So that is the smallest sigma algebra containing empty set and other thing. And if you have two collection like this, K contained in K prime, which is contained in the sigma algebra generated by that, then it is clear that sigma, see, this is the smallest sigma algebra containing this K. Notice that this is sigma of K, not K prime. K is contained in K prime, and the sigma of K is the sigma algebra containing K, and this is the smallest sigma algebra. Okay, and this is the sigma algebra containing this K prime, so there should be nothing between these two. So that is the smallest sigma algebra containing this K prime also. So sigma of K prime is equal to sigma of K when K is contained in K prime. I think it's clear. Okay. So let me erase this thing and then go to the next page. Okay, as I said, we will talk about sigma algebra generated by some collection of subsets. Okay, suppose if we have a metric space, then we can talk about the sigma algebra generated by open sets. So that is what is usually called as the Borel sigma algebra of the metric space. So that is what we will be dealing with. We will be dealing with metric space generated by open intervals. So open intervals are open sets, both are same because of this property. This property says that if something is contained, I mean, the collection of all open set is not closed under complement and other things. So that's not sigma algebra. So so the sigma algebra generated by all open set is called what is called a Borel sigma algebra. Okay, and we usually denote it by this. So this is, I mean, you should have a metric space to do this. Okay. And you can take X to be R. So what's the time? It's 32. Okay. So you can take all this semi-closed interval AB like that. Then you have, so of course you can take this collection, the I to be the collection of all these intervals like this. Then the algebra generated by this is what is precisely here. which is all those finite union of those things, collection of all this finite union of these things. That is what is the algebra generated by that. You can define algebra also exactly similar to the sigma algebra. And the sigma algebra generated by this is something complicated. I mean, we will not be able to see here the algebra, we have given all the elements here, which is not very complicated. But the sigma algebra generated by this can be complicated. So we cannot be able to list down all of them.
Sir,
Yes.
Does the Borel sigma algebra make sense for any topological space?
Yes, you can take the collection. I mean, it's yeah. I mean, this is for some convenience. We say it's a metric space or something. You can say any topological space, and you can take. I mean, it's just the sigma algebra generated by open source. That's all. There is nothing particular about metric space or something. Okay. Okay. So if you take any topological space, then you can take the sigma algebra generated by open sets. So which is the smallest sigma algebra containing all open sets. So if open set is there, then closed set has to be there. If you have open set, then the countable union of open set has to be there, which is what is called G delta set or F sigma countable intersection of open set has to be there, which is what is called a G delta set, and countable union of closed set has to be there, which is called F sigma. And you can combine closed set and I mean, it can be very complicated. It can be complicated, and you have all those collections. Okay, so that is what the Borel sigma algebra is. So here, what he says is. And so if you take the collection of all this semi-closed interval, closed in the left and open in the right, okay, then we have already seen that you can take countable intersection of these things. So he starts from, as someone pointed out, this for this to be done, you need a minus 1 by n. Yeah, you can take a minus 1 by n. So then for that you don't need any condition, I believe. So you can take the tail like this, then you can take the intersection like this, then you get the, I mean, using open intervals, you can get the closed interval. But you using this half closed interval, by taking this union, you can get this open interval AB. A plus 1 by n. This is not correct, no? If you take a plus 1 by n, you have to take union. I'm sorry. I said intersection sometime back. I was wrong. I'm sorry. This has to be union, right? If you take the union, you get a plus 1 by n. Someone, okay, nobody pointed out. So I made a mistake last time. I said it is intersection sometime back. It has to be actually union. Okay, you have to take a plus 1 by n b. Then you take the union of all this half closed interval. You get the open interval, but you will not get a. Because I mean, something is here means it has to be in one of those things. So that means it should be greater than a by something. Okay, but you will get all of them. All this, if anything is greater than a plus a, but smaller than b, that will be contained in one of them. Okay, after some time, it will be between a and a plus 1 by n. So because of that, it is. I mean, it will be greater than a plus 1 by n. If something is greater than a, it will be greater than a plus 1 by n after some time, after some n. So because of that, it is in one of those sets, so it is in this union. So the union of this, I said intersection, it has to be union, of course. So it is the union of this collection is AB. So if you take the sigma algebra generated by all these collection of half closed, half open interval, then that contains all open intervals. So it will, I mean, similarly, you get all closed interval. And you have all those union of open intervals and union of closed intervals. Okay. So today I may not have much time to define what is a measure and other things. So anyway, I will send you this file. You can read it also. I will do the other things later. So if we have a sigma algebra, so this is something like what is called a sub-sigma algebra. If you have a set X and if you have a subset X naught, then using a sigma algebra, I mean a collection of sigma algebra of collection of subset of X, you can get a sigma algebra, you can restrict that sigma algebra to X naught. So that is what is this. Okay. This is a sigma. So you just take the intersection with you take the all sets in the sigma algebra E, script E, and just take the intersection with X naught. and that will give you a collection. And that collection, you can prove that that's a sigma algebra. You can prove that that's very easily that's a sigma algebra. But then that is a sigma algebra. So that is a sigma algebra. And that is a sigma algebra generated by this K0. So for example, if you have a collection K, so this is a exercise you have to do. So I leave this also an assignment. I have already given one assignment. This is another assignment. This is very easy. I will tell you how to do. First, you have to do the following. I mean, actually, the hint is already given. That is precisely the hint. So what you have to do is the following. You want to prove that first. So whenever you want to do that something is a sigma algebra, you want to prove that something is contained in the other thing. You can prove that you can prove that the generator is contained in that. So it's enough to prove that if some generator is contained in that, then the sigma algebra generated by that will also be contained in that. Okay. So to prove the converse, this is or then you have to prove the converse. You show that some collection is a sigma algebra. So this collection is a sigma algebra. That is what is being proved here. Okay. So I have only 5 more minutes. So I think I will not. I will start the definition of measure in the next class. Okay. So if you don't understand something or if you have any doubt or something, you can ask me. And so another thing is, I will ask you to present something from the maybe. I mean, all of you have to present. There are nearly how many participants are there? There are some 21, I think. 21 of you. So, we may not be able to do it during the class time. So we will do it. We may have to take some other time to make you to present something. So for that, I will give you a choice, and whoever write it in the chat first, then I will, or you can discuss among yourself and fix who will do what. Okay. So if you have any doubt or something, then we have only 5 more minutes. So, or I can define what is a measure. You want to ask?
So when will the presentations be?
So either if you have time, we will do it on each Thursday. Otherwise, we have to do it. We have to do it through extra time. Some other time we have to fix it. Okay.
So like presentations in every week?
Yeah, maybe. Depends on how much time we have. I mean, we don't need a long presentation, some 15 minutes or 20 minutes. So we can do it during the class itself. And then we can continue the class. So if we don't have time, that depends. I mean, this is the first time I'm trying these things. So I haven't first time I'm taking a Zoom class. Last semester I did, but that's for a short time. So this is the first time I'm giving a full-fledged course through Zoom. So this is an experiment. So I have to check. I don't know. Okay. So we'll see.
Sir, when you will get your iPad and start writing, will you be giving like these typed notes or?
Yeah, I will write it, and hopefully my handwriting is okay. So I will send you the file.
Okay.
You can take notes, of course. When I am writing, it will be slow. So you can take notes also. It's not okay. I mean, you will be able to take notes when I write it. Here it's printed, so it may be fast and you may not be able to take notes. So when I write it, it may be possible for you to take notes, or I can send it to you, what I have written. Okay.
And assignments you will take before the mid-sem?
Yes. I mean, it's better you send it each week or something. I mean, if you give the collection later, it will be difficult for me to correct. So, I mean, it's just 2 problems. Each week, if you just send it, you write it, scan it, and send it through me to me by email now for the time being, before I start using Moodle. Okay. When I create the course in the Moodle, I just looked at it last week. I didn't understand head or tail, but I think it should be possible. So I will start the page and then you can submit it in Moodle. Okay.
So are these assignments graded?
Yes, of course. Yeah.
Okay.
Yeah.
Sir, and one more thing. Do you recommend any textbook for this course?
No, you can. There is a book by Halmos which is very rigorously written. Okay, but if you are very interested, you can look at it. Okay, that's very general theory. We don't need such a theory because this is not a course on measure theory. We want to introduce measure theory, then we want to move to functional analysis. Okay, this is not a course on measure theory. So we don't want to go in detail, ring, semi-ring, all those things. We don't want to introduce those things. So if you want to look at in great detail, you can look at Halmos. There is a book by Sundar and Shiva Atreya, which is mentioned in the CMI website. You can look at the course detail and the syllabus is given. Below that, there are some books written. So there are some books provided. You can look at those books. Okay, that is one thing.
Yes.
And this is, and if you search the net, so many people have given courses on measure theory. You will find hundreds of notes. Okay, whichever you find suitable, you can. In every university, in my math department in US, a course is given and they have provided the notes. Okay, so I don't have to create a notes. You can just look at any of those notes. Anyway, that's why I'm not writing a note. This I have taken from somewhere. So you can just look at that. Whichever is looking nice, you can take it. But anyway, I am providing my notes, handwritten notes or something. So you can look at that also. So there are too many books. You can look at any book you want. Okay.
Yes, sir. Thank you.
So I have a question, sir.
Yeah.
Will there be a Moodle page for this course for the rest of the course?
So that is, I told you, when I start using Moodle, I have not used Moodle till now. So I only to upload the grades I have used. So I looked at it, I didn't understand anything. So I will look at it and learn it this week or next week. Then I will start the page. If somebody helps me, then it's easy. But I have to start the page. So I will start it sometime. Then you can submit assignment, everything there. For the time being, this is okay. This is convenient. Through email, I send you the link and we don't need it. When I start the Moodle page, you can upload it there. Okay, we can communicate through that. Okay.
Okay, sir. Thank you, sir. Yeah.
Okay, so it is there something in the chat? Let me look at the chat. So someone says, so Saknik Mukherjee, a limited data pack is almost up, so I am enforced to leave. Okay, so I will look at the notes. Okay, I will send you the notes. Okay, he's not there, I believe. So I will send the notes anyway. And this is something I don't know how I can help you. So you have to get the data pack. Okay, or you can come all the way to CMI. I mean, I don't know whether food is there. Hostel, I don't know whether it is allowed. Okay,
It's not allowed.
it's not allowed. Okay, okay. So this thing, if you have any issue, you can tell me. I will raise it with the director or somebody. Okay, we have been discussing these things. I think you are also discussing in some meetings with the director or Madhavan, Dean, Madhavan, who is the Dean. Otherwise, I will talk with Rajiva or someone. If you have any issue with you are not getting something. I mean, I don't know if you are in some remote place where the net connection is not proper. I don't know how that can be solved.
So like many of us have internet connection, but I mean the best internet connection is also not very stable. So
yeah,
the
so that's why.
The problem is not the best case scenario, but the worst case scenario is very unstable. So
that is why I will try to give my notes, but I don't know how I am actually giving this class. It's from my home, so I don't know how to do that. I mean, that thing you have to sort it out. If you have some idea, you can tell us. We can.
Will the videos be uploaded as well?
So video I will try to upload. I have recorded it. So I said that is one thing. I'm thinking of going live in YouTube, but I don't know. I mean, if it is good enough to put it in the YouTube, I don't know. But I am recording it. So I have to stop it sometime. So so once I leave, it will be automatically stopped, I think. So yeah, I'm recording it. I can send you the recording also. I don't know how to send it. I can put it somewhere in the YouTube.
Yeah, on YouTube or Moodle, both are fine.
Yeah, Moodle, it's possible in the Moodle. Then I will do it in the Moodle. Okay, yeah. So that's also another.
If you're storing this recording in Zoom Cloud, you can just send the link instead of uploading.
Correct. That's also I can do. Yeah, correct. That's also I will do. So since this is the first time I'm recording, so I will see where it is recorded. If it is recorded in my computer, then I have to think how to send. If it is recorded and if it is available in Zoom, then I haven't checked. So I think it can be maybe in the Zoom. If it is there, then I will send you the link. Okay.
But the link stops working after 1 month or so something.
Say it again.
There is a finite amount of memory in the Zoom slot. So after 1 GB or something, it will you can add any more videos.
Okay, okay. So yeah, of course, my laptop also has only finite amount. So I may have to upload it in YouTube and delete it. Maybe I will keep it as a private video or something. Okay, yeah, something will be done. You can get if you can't attend a class, you can look at it. Okay. So I am happy that you are interested. I mean, people usually, hopefully you will not bunk the class and you will attend it. Okay. Many people bunk. I usually see the number of students reduce. So, okay. So if you are interested, then I will certainly try to upload it somewhere. Okay. Okay, then.
Sir, yeah, sir, please.
Once again, I will stop.
Okay, can you once again remind which are the problems for
Read again.
today's assignment?
Oh, I gave two things. One is the A or A, and in the notes it's there. There is a collection of subset where A or A complement is countable. So show that it's a sigma algebra. The another thing is you restrict to a subset. You take the intersection with the subset and show that, and that's a sigma algebra. That is easy to verify. But we have to, so I closed the file, unfortunately. So there is in the end, there is if you have a set K and if you have a subset K naught, then you can take the intersection. Then you take, if you have a collection K and if a subcollection K naught of a subset, then you can take the intersection of that. Then, oh my God, that's not the right thing. If you have a set X and you have a collection K, script K, then you have a subset X naught. Then you take the intersection of all those sets in K with the set with the subset X naught. Then you form a new collection of the subset of X naught. Then there is a connection between sigma algebra generated by that and generated by this. Okay, so that is what you have to prove. And the hint is precisely given there. That's what I am going to give as hint. So use that and prove that is the sigma algebra. It is there in the. I will mention it in the email when I send you. What is the assignment? Okay. Okay. Okay.
What is summation written of the assignment?
Say it again.
What is the deadline of submission for this assignment?
It's better you submit. I'm not very strict in these things, but you submit it within 2 weeks or something, so that when I give new assignment, it will be, it will be followed by a new assignment, and then it will be easier for you. Okay, but it should be given before, submitted before midterm. Okay, but you don't take it till midterm. You can submit it whenever it's given, next week or something, you can submit. Okay. So it depends on what are all, other courses people might have given you assignment and other things. So, okay. So in 2 weeks.
Sir, when are you giving the presentation topics?
What is presentation of topic? What do you mean?
No, like you said, like we will have weekly presentations.
Oh, that I will start from, I will tell you from next week. Okay.
Okay.
So, each one I haven't decided. So when I decide, I will tell you. Okay.
Okay, another query, like in this course, are we going to do complex measures or spectral valued measures?
Sure, we are going. Spectral valued measure is for the next semester. That is what is spectral theorem. That is what spectral theorem is about. So that I will give in this graduate analysis 2, which is actually not included in the syllabus, but we will do in the next semester.
Okay.
But complex measure we will do. Hopefully, because the time is less, no. So we will see. Hopefully, we will have time. And we will do complex measure, Riesz representation theorem, everything. Okay. Whatever in the syllabus, we will do. Okay. It's mentioned in the syllabus. Okay, so I will